Welcome and hello YouTube. So just to do our usual announcements, the reading for today is the end of chapter 8. So today is the end of chapter 8, which is not on the exam on Monday, which I know is just like a sure way to reduce attendance and have everybody just watch this on YouTube later. So hello future people. Welcome to catching up on chapter 8. So the reading for 1 week from today is all of chapter 9, sections 9.2 through 9.4. That'll start. I'm not sure. I have to admit, I was going to say, well, because of the pandemic, we're running late, but in our plan, which would be totally reasonable. But actually, I have to admit, we were actually exactly the same place last year, and we just couldn't quite cram in this last bit of stuff because it's so awesome that I really want to do it. But at the very least, we're going to be able to state a problem. That is computing what's called the discrete Fourier transform of a signal, and at least we'll at the very least be able to sort of state the problem and sort of state the theory behind it, and then hopefully we'll at least be able to spend a little bit of time on the solution. Anyway, but sort of more importantly, I think this deserves like a red pen here. So we have a problem session on Friday from 10:30 to noon, in which case, by popular demand, I mean, okay, nobody actually has asked me about this, but I will do this. Tell all your friends, we will spend the problem session discussing the sample exam. We'll have an honest to God review session, and I'll do the problems on the sample exam. I'll maybe duck out every once in a while and check on the other folks, but mostly it'll be a review session. So yeah. So tell all your friends. We will. Maybe I'll tell all your friends by email that we'll discuss the sample exam on Friday, and we are going to give it a shot of this sort of in-class exam on Monday, April 27th. Again, actually, tell all your friends if you're in contact with anybody in class that they're like avoiding class. Like, oh my God, I'm so far behind. What am I going to do? That if you're just really far behind, or especially if you have some sort of circumstance going on in your household that makes it tough for you to have been caught up, I'm going to do my best to sort of arrange for you to get caught up and maybe do some kind of makeup. But still, as many people as possible, we're going to try to do an exam on Monday, and we've gone through the procedures quite a bit, and so here goes nothing. I think it should be okay. So are there any questions before we go on? Are there any questions about sort of where we stand right now in the course and sort of what's going on, or we good to go? So actually, now that my picture is part of this thing on YouTube, you can see me listening to the clock with my eyebrows like this. Okay. All right, let's do some math. Where were we? Okay. All right. So previously, we were talking. Yes, we were sort of tackling the problem of figuring out good cyclic codes. And so remember, a cyclic code, a cyclic code, underline. Oh yeah, I should use this underscore thing more often. A cyclic code is, I wonder if I can actually just use italics here. Does that work? No, they all become italic. Okay. A underscore cyclic code is a code invariant under permutation of coordinates, which does not sound like the most promising way of a property of a code. Like, why should it matter at all? Like, why should it make a difference whether a code, whether you can sort of rotate the coordinates of a code and still preserve the code? It turns out that cyclic codes are useful precisely because you can study them using algebra. And here they are. And here's the sort of main theorem. So if C is a cyclic code of length n over FQ, and I thought I changed this, but okay, that's fine. I really was thinking F2, a binary cyclic code. Oops. Then C is an ideal, expressed in polynomial notation, is this exactly the same thing as an ideal of, oh, and I made the same typo again, an ideal of, sorry, of f2 bracket x mod x to the n minus 1. Oh, I forgot to fix that typo from last time, my bad. In fact, it is the case that C is actually also a principal ideal. The principal ideal generated by g of x for some polynomial g of x that divides x to the n minus 1, and the dimension of C is equal to n minus r. Oh, I didn't say what r is. This is what I get for doing this late at night, huh? Where r is equal to the degree of your polynomial g. So in other words, the bigger your degree of the degree of your polynomial, the smaller the dimension of your code is, which means, and remember, you want a error correcting code to have a higher dimension, because the higher the dimension of your code is, the more information your code, the more efficiently your code transmits information. The ratio of information bits to transmitted bits becomes larger. So we want so anyway, so given f2, there we go. How can we choose some length, positive integer length, little n, and some g of x dividing x to the n minus 1, such that the corresponding cyclic code generated by g of x has both a relatively large dimension. We prefer to have a large dimension to have so we can transmit more information per bit that you actually send. Remember, because for example, the repetition code, as you may remember, corrects lots of errors. It's very good at error correcting, but it's very inefficient. You have to transmit lots and lots of bits for every one bit of information that you send, and a large minimum distance. And the reason that we care about having a large minimum distance is that we have, remember, this gives you more error correction. Right, so somehow we want this magic combination of being efficient, of being cheap. I guess it's not really so much a matter of being efficient here. This is like, what we're really saying here is that we want to save some money, right? I mean, we want to save money. Yeah. So oddly enough, I mean, maybe this is almost like too applied. It doesn't sound good. Is it so applied? But basically, you want to be a cheapskate. You want to spend less money for every bit of information that you send, and so that essentially means you're having a large dimension. And we also want to have more effective product. We want to have more error correction. So this is sort of the balance of error correction. Oh yeah, so right. So John V asks, this is the balance of error. So this is the balance of error correction. John V, let me get your question. This is the balance of error correction before having good error correction versus spending less money. So John V asks, in 8.2, we assume that x to the n minus 1 is equal to 0. So how can we divide g by x to the n minus 1? So it's sort of the other way around. This is relevant. Remember, it's relevant because there's always this unfortunate linguistic ambiguity of, it's not that we divide. So what do I mean by this? So let me remind you of the word, linguistically, what the word divide means here. This means that x to the n minus 1 is equal to some like f of x times g of x. So sort of mod. I mean, I guess, so I mean, there's two answers to that. There's sort of more subtle answer, but really kind of bogus answer here is that this is happening in this idea that g of x is dividing n x to the n minus 1. That's happening in the ring of just the ring of polynomials without modding out by x to the n minus 1. So we sort of think of that dividing as happening before we set x to the n minus 1 equals 0. But this even sort of still makes sense in mod x to the n minus 1. It's really think that g is a 0 divisor in that quotient ring. So yeah, and so I think it's always the linguistic confusion is that unfortunately when we say that g of x divides n minus 1, it's more like the x to the n minus 1 is on top and the g of x is on the bottom, not the other way around. Oh well. Yes, trying to do math in English is a cruel linguistic business. All right, so okay, we answered that question. Okay, great. So any other questions about? I think that's it. Yeah, okay. That's our sort of initial review, and then we'll review a different thing and get back to that. So is everybody's good with this setup so far? So we want to find a g of x that is a factor of x to the n minus 1, such that that somehow magically the sort of corresponding cyclic code of length n is both cheap and effective. Okay. So next. All right. Oops. Wrong way. All right. So okay. So yeah. So we kind of, I think maybe we kind of left off in an awkward place last time. So so this is so the sort of motivation for the stuff that we started talking about last time and that we'll finish talking about today is the BCH theorem, which we can think and we will not talk about its proof at all in class. I mean, for a proof, see the book, but you can just take this as being a fact, a sort of a fact of nature, and the details of the proof are beyond the scope of this class. Oh, there's the typo is still here. My goodness. All right. So let's see. Oh, goodness gracious. There we go. F2. So let's see the cyclic code of length n over F2, and see, and we're generated by some polynomial g of x that divides x to the n minus 1. And suppose suppose E is an extension of F2 such that for some positive integer delta and some alpha in F and E in the field capital E and so here what we really want to think, i.e. E is equal to F, is equal to FQ, where Q is equal to 2 to the little e. Right, so when I say field extension, we should really just think, well, E is one of these FQs. And suppose suppose alpha is some element of E, where the order of alpha is exactly equal to n. And suppose also that we have alpha let me just rephrase that, alpha and alpha squared all the way up through alpha to the delta minus 1 are all, each of those elements are all roots of little g. G will have other roots, but the point is that if you plug each of those elements into the little g, then you get 0. So if that's the case, then the minimum distance d of your code is at least delta. So for example, if for example delta equals 5, which is a sort of common example that we'll see later today, C corrects 2 errors per code word. So remember, we saw back in our chapter on codes, chapter 6, we saw that if basically that if your minimum distance is at least 3, then you correct 1 error. If your minimum distance is at least 5, you correct 2 errors. 7, you correct 3 errors, and so on. That was that floor floor. The number of errors the number of errors corrected is the floor of d minus 1 over 2. I don't know if you remember that. And so yeah, 5 minus 1 over 2 is 2. Anyway, so so the point is that if you can somehow get at least so if you can somehow get at least 4 consecutive alphas, powers of alpha that are all roots of this one polynomial, single polynomial, the little g, which is the generator of your cyclic code, then the code will correct will have minimum distance at least 5. So so somehow having all these roots of g allows you, it's a fact that having all those consecutive roots of having all these consecutive powers of alpha be roots of g, that gives you a lower bound on the minimum distance of your code, which is otherwise it's something very difficult to achieve, and it's even very difficult to verify once you have your code. So here's our problem. So suppose let E be an extension of F2. Then in other words, E is equal to FQ, where Q is a power of 2. Q is a power of 2. And let alpha have be an element of the multiplicative group of E of order n. So what we want to do is we want to find, so given those facts, we want to find a little g, a polynomial with coefficients in F2 of the smallest possible degree. So remember, this is sort of, remember, the smaller in general, well, not in general, the smaller the degree of little g is, the more information you can actually transmit in your code. So what we want to do is we want to find a little g of smallest possible degree such that g divides x to the n minus 1, as we were just discussing, and g has all these roots, alpha squared up through alpha to the delta minus 1, for as large a value of delta as possible. So we want to have a big delta but at the same time the smallest possible degree g. So the key idea that we have here that makes this work is that, believe it or not, that this is like really abstracty sounding thing. Look, there's even like a person's name that goes with it, and we all know that things with people's names on them are like super important and abstract or whatever. Yeah, so we have this really abstracty sounding thing, a Frobenius automorphism, which is just, well, okay, it's a fancy name for squaring. Okay, it's just squaring an element. But this actually turns out to be an automorphism of your field capital E, which capital E is FQ, and one of the keys of that automorphism, one of the key properties is that rho of beta for and parens for any, if we assume only that beta is in E, then rho of beta equals beta exactly when beta is in F2. That is, so the only elements of E that are fixed by the automorphism rho, are 0 and 1, i.e. beta is equal to 0, either 0 or 1. Okay, so those are all the ideas we talked about last time that we're continuing to talk about today. So that is sort of this slide and the previous one. So we had the cyclic code generated by G, and we have this BCH theorem that says that this is one way to ensure that your G is effective. And so then we have this idea of a Frobenius automorphism of squaring. So everybody good so far? Or are there any questions so far? Okay. So next. All right. So now, yeah. So now we got onto new stuff. All right. So I want to talk about the minimal polynomial of an element beta. So let E be an extension of F2. So again, I want to think let E be FQ, where Q is a power of 2. So I'm gonna fix some. So let's hold one particular element beta of E constants. So we're just looking at one particular beta, and I want to let I be the set of all polynomials with coefficients in F2, not coefficients in E, but of the sort of bigger field, but of the sort of base field of the base field F2. So coefficients, we're only allowing coefficients in one with zeros and ones, and so we want to let I be this. We want to let I be the set of all polynomials of coefficients that are zeros and ones, such that f of beta equals 0. So then I is an ideal of F2, is a fact that I is an ideal of F2 bracket x. This is something you can prove, but in the usual way, you know, it contains the 0 polynomial, sure. If two polynomials have this sum, have this property, then their sum has that property, okay. And if a polynomial has this property and I multiply it by some other random polynomial, well, then when I plug in beta, I'm still going to get 0. And so I think I might have put this on the homework to prove this is an ideal. Well, I just kind of told you how to do the homework, but in a very condensed form, so that you know, you think it was at least a push in the right direction. Anyway, so if we define I to be this ideal of F2 bracket x, so if this set, the subset of F2 bracket x, then it's an ideal of F2 bracket x, which means that it's generated by some m of x. And so we call m of x the minimal polynomial of beta over F2. And I guess the reason we call it a minimal polynomial is that the point is really that m of x, oops, try that again. The point is that m of x, no. There. You know, by the end of the semester, I'll be really good at this. M of x is the polynomial of smallest degree such that m of beta equals 0. For all that, I still won't have to make this wider. Okay. Right. So the point of the minimal polynomial m of x is it's the polynomial of smallest degree with polynomial with coefficients using only zeros and ones, the smallest degree such that m of beta equals 0. And so here, so here's a common special case, and I guess right. I'm saying fact. Then, so I'm stating this without proof, though it is true. Fact. Okay, so suppose alpha is a primitive element of E, and I want to define m sub I of x to be the minimal polynomial of alpha to the I over F2. So so we have m sub I. So for example, like m3 of x is the polynomial of smallest degree such that m3 of alpha cubed equals 0. All right, so it's a fact that then the polynomial smallest possible degree that has all of these roots as all of these elements, alpha squared, alpha cubed, up through alpha to the delta minus 1 is actually the least common multiple of all the other minimal polynomials. And by the least common multiple, what do I mean by LCM? I just mean that it's you basically take the product of them without repeats, and you remove all the repeats. So if we can figure out the minimal polynomial of each given alpha to the I, then we can take the product and then remove all the repeats, and then we get the sort of g of x the smallest possible degree that will have all those things as all those elements alpha squared up through alpha to the delta minus 1 as roots. All right, so now that's the setup. So we see from what we have right there that the goal, the computing minimal polynomial, is the goal here is to compute the minimal polynomial of alpha to the I of each of those alpha to the. I mean, I'm going to talk about this in general, but the goal here. But the goal we always want to keep in the back of your mind is that we're really computing the minimal polynomial of each alpha to the I. So let E be an extension of F2. Geez, I really should have just said, instead of just saying that, I should have said E equals 2 to the E, 2 to the little e. Okay, oops. F sub Q, where Q equals 2 to the little e. That's all we're thinking about here. So let E be an extension of F2, and let B be an element of its multiplicative field. And so I'm going to define beta sub n for fixed beta. Define beta sub n. I'm going to define beta sub n to be rho to the n applied to beta. That is, I mean, that's rho of rho of rho of rho of beta. And so the idea is that we apply the rho n times. So let beta sub n be the result of applying rho to beta n times. We define the Frobenius orbit of beta to be, the set of all those betas, beta 0, which is just beta itself, beta 1, that's rho of beta, beta 2, which is rho of beta, and so on. And so now, and we want to absorb that. I want to observe that this is a fact that this orbit is always finite. That's not obvious. So that's another fact. It's actually that's actually proven in the textbook, but for our purposes right now, it's enough to observe that this is a fact. This is true. That if you, and actually we'll just see in practice when we actually compute these things that when you square enough times, you eventually get back to where you started. And here's the theorem. The thing. This is the fact that we use for the purpose of computation. If this is your Frobenius orbit of beta, here's beta itself, and then you keep squaring, and eventually you square back and go back to the beginning. You circle around, and you'll see when we get to. I'm sorry, I'm spending so much time just like stating what it is you've done, but when we actually do it, you'll sort of see how this works. So the Frobenius orbit of beta is like you start with beta and you square a bunch of times and eventually get back to the beginning. So if that's the case, then the minimal polynomial of beta over F2 is exactly the product of the things in the form x minus the elements of an element of the Frobenius orbit. And furthermore, if it is also true that if beta has order n, then m of x divides x to the n minus 1. So this is the minimum polynomial that you want. Right. Oops. And I did this wrong here. Okay, so let me talk about, gee, that wasn't what I wanted to do. So let me talk about why this is true. Yeah, okay, so before doing, I guess, yeah, I sort of planned this before, and why is this true? I just want to give you an idea. So the idea, what happens if we apply squaring to the coefficients of m of x? Well, this is what we called back in chapter 7 the induced automorphism. See chapter 7. So what happens is we have x minus beta times x minus this, and this is the same as beta sub 0, beta 1, beta 2, all the way up through x minus beta sub s minus 1. So in green, I'm going to indicate what squaring does. Well, remember the whole point is that beta sub 0 squared is beta 1, so that when you apply squaring to the coefficients of m of x, that's the same thing as because we using the homomorphism property. Oh my God, using the homomorphism property. There we go. We can actually, instead of when we apply rho to the coefficients on the left-hand side, we can actually apply rho to the coefficients on the right-hand side. And so squaring takes beta 0 to beta 1, and takes beta 0 to beta 2, and so on, up to beta s minus 1, and then precisely because we have an orbit, this must because we have a finite orbit that's closed up when we do this in the end. We actually have to end up sending this last term x minus beta sub n minus 1 back to x minus beta, and so the point is the induced. So applying the Frobenius automorphism rho to the coefficients of m of x doesn't change them. So they must be either zeros or ones because right, yeah, because one of the key ideas is that rho of beta equals beta exactly when beta is in F2. So it must be somehow there in some magical way when we multiply out all these x minus beta 0, beta minus beta 1, minus beta 2, and we'll sort of see an example of this later on today. When you multiply all this stuff out, somehow magically all that stuff cancels out and you only get zeros and ones. Amazing. But it's the power of symmetry. This is okay. All right, and now sort of algebra is my native language, at least mathematically, and then but now we're actually sort of getting to the area of symmetry and group theory, which is like my native dialect of my native language. So I apologize if I lapse into the mathematical equivalent of a strange New England accent. Yeah, I can't have it yet. But this is really like my so symmetrization. It's always like symmetrization that's sort of if you take an object and you symmetrize it, then you get a symmetric object. That when I say it sounds kind of dumb, but it's the most amazingly useful principle. When you take an object and you symmetrize it, you get a fully symmetric object. And what this sort of says is we took this object here, x minus beta, and we spun it around, and we got a symmetrized object. But the only symmetric polynomials are ones that have coefficients in zeros and ones. So there we go. All right, I don't know. That's at least the idea of what's going on. So, any questions? It's a little bit sheepish there. It's maybe a bit of an undeserved smiley. So, are there any questions? I bet you all want me to do an example of this, right? So I can do actually a pretty concrete example here. So is everybody ready for the example? Or ask questions now if you have them. God forbid we should do an example. Okay, so let's do an example. Well, it's not so secret because because I'm saying this is secretly the Hamming code again. But okay, so let's consider. So I want to compute. I want to take all these sorry. So let me just start to do what the slide says. So suppose let's let E be F8, which is an extension of F2, and let alpha be primitive root of E, which we saw before. We can take that to be in other words, we let F8 be F2 bracket alpha, where alpha cubed is equal to alpha plus 1. All right, remember this is sort of and this is let me remind you is that that we saw before, because one way to define the field F8 is it's F2 bracket x mod x cubed plus x plus 1. So remember we did that before. That gives you a field of order 8 because x cubed plus x plus 1 is an irreducible polynomial. And put in terms of the quotient, this is the same thing as saying you add an element alpha with the adjoining element alpha with the relation that alpha cubed is equal to alpha plus 1. So now, if we now want to compute the Frobenius orbit of alpha to the I, we start with alpha to the I and keep squaring until we get back to alpha to the I, keeping in mind that alpha to the 7th is equal to 1. So let's compute the Frobenius orbit of alpha. All right, ready? Here we go. This is, thank God, finally a concrete example. I know I feel like I don't want this to be totally mindless. So I do feel responsible for having put in all that theory they had before. But now we get down to it, when the actual thing that you have to do is, I hope will make more sense. Okay, so if we start with alpha and we apply the Frobenius automorphism to it. I know it's all famous. It sounds all fancy. Frobenius automorphism. What we really do is we're just squaring alpha. So you square alpha, we get alpha squared. So remember, alpha rho, the Frobenius automorphism is just squaring. All right. So let's see what happens. So let's see how well we're tracking now. So now we're doing something very concrete. We're squaring everything. So if we apply rho again, somebody want to type in the chat, what do you get when you apply rho again? So when you square again. Somebody want to give this a shot. Oh, so remember, so we're squaring again. So we start off with alpha squared. Right. So the two folks who responded, Johnny and Alexis together, just sort of, if I munch your answers together, you apply, when you square alpha squared, you get alpha to the 4th. That's right. Oops. Can I actually write this? Yeah, alpha to the 4th. All right. So yeah. So that's sort of had everything put together. There is was the answer, right? So let's try this again. Somebody else. Besides Alexis and Johnny. When you square that again, what do you get? You get, so we took alpha, we square once, we get alpha squared. We square again, we get alpha to the 4th, and we square alpha to the 4th again, what do we get? Well, okay, there's actually kind of a little trick here, but so alpha to the 4th squared is, or go ahead and answer those same folks answer again. Okay. Oh, there we go. Should I talk about? Yes, and I think I should. So the pause there tells me I should say just a bit more about this. So remember, let me actually. I'm going to do another page of scratch work here. Yeah, and Ryusei is taking this another. Yes. So here's Ryusei is taking this to another level. That's right. So remember. So but let me in case anybody was unsure of their answer. So let me remind you that rho of anything is its squared. Rho of beta is beta squared, and so rho of alpha is going to be alpha squared. Rho of alpha squared is going to be alpha squared squared, which is alpha to the fourth. And then the reason I haven't written down alpha to the eighth here is that we in our scratch work here, we have rho of alpha to the fourth, as Ryusei just said, that's alpha to the eighth. But we know that, remember, that alpha to the seventh is equal to 1 because the order of alpha is 7. So keeping in mind that from our finite field of facts, because we have a field of order 8, everything has to have order dividing 7, and there's only one thing to divide 7, which is not 1, which is 7. So the order of each of these things is going to be 7, and so alpha to the seventh is equal to 1, and so alpha to the eighth is equal to alpha to the seventh times alpha, which, as Ryusei just said, is equal to alpha. So here's the interesting thing. We now see that, that rho circles back. And so what we get here is that the Frobenius orbit, rho sends alpha fourth back to alpha, and so the Frobenius orbit of alpha, the orbit of alpha, is equal to the set containing alpha, alpha squared, and alpha to the fourth. Okay, see, once you have an actual example, it's not so bad. I mean, okay, there's a lot of terminology around it, but the thing you actually do is computing. The thing that you actually have to do to make money is to compute these orbits, and computing the orbits is not too bad. So any questions about how we get to the Frobenius orbit of alpha is equal to alpha, the set containing alpha, alpha squared, and alpha to the fourth. Excuse me. Okay, and I want to observe one other thing. So you may notice now that what happened, this action of rho on alpha and alpha squared and alpha to the fourth just goes in a little circle here, right? This is really, maybe a more honest picture of this would be you have alpha. You have alpha over here, and you apply rho to that, and you get alpha squared. Maybe not exactly a more honest picture, but I mean a better picture of this is that, and then you apply rho again, and you get alpha to the fourth, and then you apply rho again, and you get alpha, and you go back to alpha. So you have this little circle or triangle, which means that if you're looking at the orbit, and this is actually pretty important for what happens next for the application. If you start with alpha squared, you end up with the same orbit, because we all really care about is the set, not the order in which these things show up. So so the orbit of alpha squared is the same as the orbit of alpha. It's the set containing alpha and alpha squared and alpha to the fourth, and so this is also the orbit. This is also equal to the orbit of the Frobenius orbit of alpha to the fourth. In any case, so now if we now go back to, so that's an observation. Let's put that in our pocket and come back to it later. Yeah, and so right. So what the orbit theorem says is that the minimal polynomial of alpha is going to be the thing you get. When you take the product of x minus the product of the things of the form x minus some element of the orbit. And so the minimal polynomial of alpha is going to be, this is what in our notation we called m1 of x. That's going to be x minus alpha times x minus alpha squared times x minus alpha to the fourth. Okay, so that's the minimal polynomial of alpha. Now, okay, so now I'm going to do something that I will not do, and I'm going to do it maybe a little bit quickly. So just pretend I'm like Wolfram Alpha. Ha, alpha. See what I did there? So pretend I am Wolfram Alpha, and I'm just going to sit here and you type this in, and you said, okay, compute Wolfram Alpha. Tell me what this product. If you multiply all this stuff out, what do you get? So this is going to be equal to x, it turns out this is equal to x cubed minus alpha plus alpha squared plus alpha to the fourth x squared plus, as it turns out, alpha cubed plus alpha to the fifth plus alpha to the sixth. This is like not at all obvious how you got this, but it is true. And so maybe the last term makes a little more sense. In order to get a term that does not involve any x's at all, I have to multiply the constant terms of these things together, and so I get alpha to the seventh. Okay. Now let me go down here in our scratch work. Our scratch work, so we know that alpha, in our scratch work, we see that alpha cubed is equal to alpha plus 1, which means that alpha to the fourth is equal to alpha squared plus alpha. So which means that alpha to the fourth plus alpha squared plus alpha equals 0. What? And in a similar way, though I will omit the details, alpha cubed plus alpha to the fifth plus alpha to the sixth. So omitting details. If we use these same, so remember this is one thing I know we talked about quite a bit. When you compute in a finite field, you always use these reduction rules, and if you apply these same reduction rules to here and their descendants, after a while, you'll see this boils down to 1. And so when you simplify, oh yeah, and we already know that alpha to the seventh is equal to 1. And so when we boil down this polynomial, then magically this is equal to x cubed plus 0x squared plus 1x minus 1, or in other words, because minus is equal to plus, x cubed plus x plus 1. So I just want to point out that, whoa, I need a more stunned looking Keanu kind of reaction here. Whoa. Yeah. So if you really understood what just happened, when you understand what, not if but when you understand what just happened there, you should appropriately Keanu, because somehow we took this, I took this expression, which is this complicated thing involving alphas, and somehow we managed to get some kind of not well, one, we got an expression that only involves zeros, and that everything somehow simplified, and at the end we only got zeros and ones. And two, and we note that, and let me note that we know already, and we know from before, that m1 of alpha equals 0. Well, I mean, I suppose we know that m1 of alpha equals 0 because that's the way we rigged it up. Like we included a factor of x minus alpha in it. So of course, if we multiply that, we're gonna get something that has alpha as a root. But the fact that we somehow managed to do that over here, and the fact that we did that in a symmetric way, and we got something that only had coefficients in zeros and ones, that is a whoa. Symmetrization results in symmetric objects. Yeah. Oh yeah. All right. So okay. So sort of the remarkableness of this aside, all you have to do is be able to do this computation. So are there any questions about how I got this computation sort of up to what point? So I'm not gonna require you to do so I will ask you to do this orbit stuff. And I will ask you to write out that m1 of x is equal to this product, but I'm not going to ask you to do the rest of the check. Maybe I should put it in a line here. So I will not ask you to verify that what's happening under this blue line. I just did that to just show you sort of what it is that the theorem is exactly what it is that the theorem is saying. You won't have to do that on the homework or on an exam or something. You just have to get down to the blue line. So are there, and then the theorem just says that what you have there will have some polynomial involving only zeros and ones, which is just a remarkable thing. But you won't have to go ahead and check that. Maybe I have to do that once on the homework, but okay. All right. So that being said, are there any questions about how to start with alpha and this task of finding the minimal polynomial of alpha and get down to the blue line? So are there any questions about that, or are we? So can you say yes, we're good to go on? You're good to go on for now from that, or ask a question in the chat. So either yes or question in the chat. All right. So I think that's a couple of yeses and maybe a lot of like, oh, I'm just going to have to go back and look at this one in the video, dude. That's all right. That's why we have the video. Or, when we get to the homework, we'll sort of see this all again. Okay. So now let's go on. Let's go on to the grand finale. Like, what is the point of all this? Oh, yeah. Okay. Sorry. One other. Let me do one. I'm going to do one more example. Yeah. I'm going to do one more example and make it a little faster. So I want to find the minimal polynomials of m1 of x, m2 of x, up through m7 of x. Okay, so now I'm going to go a little faster. And orbits. Alpha, and so remember, oh yeah, so alpha is primitive, which means that alpha to the 511, or alpha is order 511. In other words, alpha to the 511 equals 1. In other words, alpha to the 512 equals alpha. And so the first orbit, the orbit of alpha, which is equal to alpha squared. You know what? I'm just sort of tired of writing alpha all the time. So I'm going to introduce the following abbreviation. Oops. Yeah, especially since we have a little time. We need a little time here. So the orbit of alpha is, I should do something like a bracket. So it's alpha to the 1, alpha squared, alpha to the 4th, alpha to the 8th. So this is, I hope you see this is an abbreviation for, this is alpha to the 1, alpha squared, and so on. So but all you're really keeping track of are the powers of alpha, the exponents of alpha. So you just really need these numbers: 16, 32, 64, 128, 256, and now alpha to the 256 squared is alpha to the 512, which is equal to alpha, and so that circles back to 1. So 1, 2, 4, 8, 16, 32, 64, 128, 56. Those are the powers of alpha that are in the orbit of alpha. And because 2 and 4 already showed up here, this is also equal to the orbit of alpha squared and the orbit of alpha to the 4th. Okay, so now, so this actually already gives us the minimal polynomials of alpha. So this is m1. So the corresponding m1 of x is going to be x minus alpha times x minus alpha squared times x minus alpha to the 4th, all the way up to x minus alpha to the 256, and then the orbit circles back around, so we're done. And that's the same thing as m2 of x. Oops, a little excited there. M2 of x, and it's also the same thing as m4 of x. So yeah, so it maybe didn't look so helpful that I was going to sit here and do 7 of these things, but it turns out it turns out that you can do 3 of them at once. So there's a reason why I asked for that. So are there any questions about how I got m1 of x and why it's equal to m2 of x and m4 of x? Okay. So that's m1. So now we've knocked out m1, m2, and m4 of x. So the orbit of alpha cubed, again, let me use this bracketing notation. It starts with alpha cubed, alpha to the 6, so 3, 6, 12, 24. Oh my God, can I actually double on camera and do this correctly? Catch me when I mess this up. Squared is 40, alpha to the 48, 96. Oh God, 200 minus 8 is 192, and then 384. Oops. 384. Right, and so let's see. Let me. So 384 doubled is 768 minus 511 is 257. So yeah, so here's an important thing, and this is always very confusing. So because that's not what I want to do. Yeah, but actually, let me type this instead of finger writing it. Because Q is equal to 512, we have it working in a field of order 512. The exponents are all done mod 511. So that's super important and a little bit confusing. And so this is the point. The way that we got from the 384 to the 257 is that 384 times 2 is 768, but then mod 511 is 257, because then 257 twice 257 is 514. Mod 511 is 3, and thank God we circled. I did that correctly. We circled back. So that's the orbit of alpha cubed, and similarly the orbit of, and so that actually gets, and so that actually checks off. That actually gives you not just m3. So this gives you m3 of x, but also m6 of x. So now we have the minimal polynomial for 1, 2, 3, 4. Let me go back to red. So the only thing that's left now is alpha to the 5. Well, alpha to the 5 and alpha to the 7. Let me actually, oops, I keep leaving myself in. Let me change what I was doing, and let me make this. I'm only going to go to alpha to the 6th here. So alpha to the 5. Let me do one more example. It starts out 5. Thank God this is a little easier to multiply. 5, 10, 20, 40, 80, 160, 320, and now we have 640. 640 mod 511 is 129. That's right. Which doubled is 258. There we go, and that circles back to 5. Because 258 doubled is 516, mod 511 is 5, and so this and that and sort of doing our usual symmetrization, this will give you m5. Oops. Okay, so are there any questions about that process of finding a Frobenius orbit, finding a Frobenius orbit, and then sort of turning it into a polynomial? Okay, so where am I? There I am. Okay. All right. So so let's look at this theorem again. So the BCH theorem says that if we can find a g of x such that g of alpha such that alpha is a root of g, and so is alpha squared and alpha cubed up through alpha to the delta minus 1, then the cyclic code course generated by that polynomial will have minimum distance at least delta. And so a code of this form is called the BCH code, and if C is a BCH code, we call delta the design distance of C. And the reason we call this the design distance is that the actual minimal distance may be bigger. The actual minimal distance of your code may be bigger. So if we're going to get a BCH code of design distance delta, what we want to do is we want to find the smallest possible degree of polynomial g of x divisible by x minus alpha and x minus alpha squared, all the way up to, oh, my daughter says hi, up through, it's messy over here, alpha to the delta minus 1, should be that last term, sorry about the typo, which again will be, I know there's a text function, it doesn't have alphas in it, yes. That's it. Hi, YouTube. Working from home is so much fun. All right. So we want the lowest possible degree of polynomial divisible by all these terms alpha x minus alpha through up through x to the minus alpha to the delta minus 1, which will end up being the least common multiple of the minimal polynomials. Oh, hey, Ryusei, what's up? Ryusei, did you have a question? Did you have a question? Or you're just raising your hand? You hit the raise hand button by accident. Ryusei, I'm gonna unmute you and see if there's something you want. Oh, you're just typing. Okay. All right. So okay. So sorry. So the point is that if we want to find well, you'll see what in practice. Say if we want to find a BCH code of minimal distance 5, then we want to do. So yeah, let me write that out. If delta equals 5, we want the least common multiple of M1, M2, M3, and M4. Whoa. Comma, and oh, that's the page down button. Comma, M4. Goodness. Right. So there, I think that's easier to see in a concrete example. If we want to design minimum distance of 5, then the g that we take will be the least common multiple of M1, M2, M3, and M4. So here, keeping that in mind, here's a recipe for BCH codes algorithm. So choose an extension. Here's a better way to put this. Let E be f sub q. Oops. F sub q, where q is 2 to the e. And so choose alpha and e and let n be the order of alpha. And usually, often what we're going to do here is we're going to let n be q to the e minus 1 and then let alpha be a primitive root of e, which we always know there is a primitive root of e. And so our code is length n. And so we'll get back to this step. I want to I'll point out the importance of this step later. Sort of, it's a little bit weird. So then we choose some design distance delta, like how many errors based on how many errors we want to correct. So if we want to correct, for example, we want to correct 2 errors. If we want to make sure that we correct 2 errors for every code word, then we take delta equals 5. If we want to correct 3 errors for every code word, we're going to take delta equals 7, and so on. Right, so that's the thing we choose is delta, and then let g of x be the least common multiple of those minimal polynomials, m1 through m sub delta minus 1, and then if we do that, then C will be the cyclic code of length n generated by g of x. So that's how we get a good code that's how we pick a good generator for a good code. Now, so here's a weird thing. And actually, this is, let me pull out a bit to show you this whole page in order to point out the weird thing that happens here. So the weird thing about this is that in step number 2 here, we don't actually choose the length of our code. So like if you're sitting here and you're designing some sort of communications protocol, and you say, I want to have a good BCH code, that an effective BCH code of some that has a certain error correction properties, you don't actually get to pick how long your transmitted code words are. Nature, the universe you have to let the universe do that. So you can't. I mean, you can pick the field that you use. You can, well, you sort of get to pick n, but but you don't exactly get to, sort of once you pick your field that you use, n is basically going to be the number of elements that field minus 1. So in general, I mean, you can get slight variations in this, but generally, if you see a good BCH code, so for example, so one of the weird things about this, how this construction relies on nature is that good BCH codes usually have length 2 to the e minus 1, so some power of 2 minus 1. So if you look up BCH codes in Wikipedia, there's a very nice entry about them in Wikipedia. You'll see they all have like length 31, length 63, length 127. 2 to the n, 2 to the e minus 1. All right, so let me do an example. This is an example of F8 with alpha primitive. I think you'll be unsurprised to see this is, well, it's the same example we always have. Let delta equal 3. So we want, so the point of this is that we want, let me pull out again. We want to have g of alpha. So in order to get delta equals 3, we want g of alpha be equal to 0 and g of alpha squared equal to 0. So what we want is we want the least common multiple of the minimal polynomials of m1 of x, and m2 of x. Right. That 2 comes from the 3 is because 2 is 3 minus 1. And so remember that and this will also give us that d. So this is also going to give us that d is at least 3. So we're going to be able to correct one error. Okay, so that's what's going to happen. So the orbits, well, the orbit of alpha, the orbit of alpha is going to be equal to, I want that to be a set, alpha to the 1, alpha squared, alpha to the 4th, and then remember, because we have a field of order 8, we have that alpha to the 8th is equal to alpha, and so that circle, and so this circles back around, and we get, and that's the end of our orbit. So, that's also the same as the orbit of alpha squared, because alpha squared shows up there too. So our g of x is going to be equal to x minus alpha times x minus alpha squared. Hey, we know this, right? Times x minus alpha to the 4th. So our generator is going to be alpha cubed. As it turns, it's this. The generator is that. Which, as we saw, turns out to be x cubed plus x plus 1. That's not obvious, but it's true. So again, what do we get when we apply the BCH construction to this? In this case, in this sort of small, interesting case where where E is the field of order 8, then we get the Hamming code again. It's, this is sort of like such a God-given object. Like wherever you go, you're just going to end up turning up the same example again. So by now, I think I hope it's sort of not a surprise to see that when we start with a small example f8 and we sort of apply basically any construction around like size 7 or 8 is going to turn up a Hamming code. Any quick questions about? I want to do one more a more interesting example in a minute. So, but are there any quick questions about that so far? Okay, so let's click over here. Okay, there we go. And now, so let me do one more example. And this is actually and then maybe if I have a minute, I'll talk about some consequences there. So so what we're going to have our generator. Remember, our generator G is going to be. Let me start by. Oh my God, my hand looks so huge when I reach over there, huh? I'm gonna start by, this is gonna be the least common multiple of, because we have delta equals 5, delta minus 1 equals 4. All right, so the generator is gonna be the least common multiples of M1, M2, M3, and M4. So, so again, to get a minimum distance, a design minimum distance of 5, oops, I'm so excited about 5, I wrote in the number 5 there for some reason. So in order to get a design minimum distance of 5, you go out to M4. So so over here, we want to calculate the orbit of alpha, which contains alpha squared. Oh, right, and here we have alpha to the 31. Alpha is primitive, so alpha to 31 is 1 alpha squared, alpha to the 4th, alpha to the 8th, and alpha to the 16th, and then we have alpha to the 32nd, which is equal to alpha. And so we have 1, 2, 4, 8, 16. And so so this gives, and this is the same as the orbit of alpha squared, and it's also the same as the orbit of alpha to the 4th. So actually, we're almost done. All we need to do is figure out the orbit of alpha cubed, and that is alpha cubed, alpha to the 6th, alpha to the 12th, alpha to the 24, alpha to the 48. 48 mod 31 is 17, and alpha to the 17 squared is alpha to the 34th goes back to alpha cubed. Great, so I didn't mess that up. So we see, so there we get one. So one of the orbits is 1, 2, 4, 8, 16, and the other orbit is 3, 6, 12, 24, 17. So M1 is x minus alpha times x minus alpha squared times x minus alpha to the 4th times x minus alpha to the 8th times x minus alpha to the 16th, and then that's equal to M2 and M4, and then M3 is alpha x minus alpha cubed, and there's another 4 terms after that, ending up with x minus alpha to the 17. Right, so you would copy these elements up here, down here, and so g of x is going to be equal to m1 of x times m3 of x, which means that the degree of g is 10. So let me skip, for time, let me skip the delta equals 7 case. So if you write down the details for that code, and so this has, so the dimension is going to be equal to the length, which is 31, minus the degree, which is 10, which is 21. So this is, so sort of skipping through here, skipping the delta equals 7 example, which is pretty similar. So we just saw that g of x equals, it had x minus alpha squared, and there's sort of 5 terms here, and then we had x minus alpha cubed, and x minus alpha to the 6th, and 31 terms here. And so that is going to equal to some polynomial degree 10 of degree 10 with coefficients, as we saw earlier, in 0s and 1s. So again, just like we did with in the case that produced the cases that we produced the Hamming code, but in some way more complicated sense, we multiply all this junk out, and we keep applying alpha to the 5th equals alpha squared plus 1, and reduce, and then somehow all these coefficients will turn out to be 0s and 1s. Amazing. And so and then we turn the coefficients of G into a vector and rotate that thing cyclically to get a generator matrix. All right, I've already like 2 minutes over, and so I've definitely worn out my welcome, especially when I've uttered the beginning, started this class by uttering magic words. This will not be on exam, so sorry about that. Anyway, so thank you very much for your patience. Remember, on Friday from 10:30 to noon in the problem session, tell all your friends, tell everybody that we will spend the problem session going over the exam and taking questions if there's any time left. Bye, YouTube.